How many? Okay, so I'll just go through the problems and you kind of identify. Let's try to identify, some representative ones that you'd like to go through. Can everybody see this one? Limit of x sine x as x approaches 1/2. Yeah. Is that hard or easy one? Real easy. How come? Plug it in. Absolutely. This is one where, remember, and don't lose sight of that. I think sometimes in math, we tend to work on the skills that we need the most practice on, and sometimes the problem set gets to a point where a lot of them are indeterminate. And so you sort of fall into the pattern of just assuming that problems are going to be indeterminate, 0 over 0 kinds of things, and that one's not. Just evaluate it, and get an answer, and you're done. Okay, how about this guy? You see that? Let me grab this one. Even if we don't talk a lot about it, I want to just take a quick look at it here. Okay, what about him? What do you think?
I know the answer. I just not sure why.
Okay, yeah. Let's kind of talk about how two things about why the answer is what it is, and also I want you to pay close attention to this. And I'm making a video of this, so you can always go back to it. What the work looks like. How do we organize the way we approach this on paper? Okay. Talk to me about this one. What do you know? Well, what's the standard form of the limit? What's our little special limit that we're going to fall back on here?
Sine x over x.
Okay, good. Sine, the limit of sine of whatever you want to call it. X is fine. Sine x over x as x approaches 0 is what? 1. Okay, so there's the form that we're going to rely on. We've got to coax that out of this limit. Talk to me about how we can slice and dice this thing and have that pop out.
Square root of 6 times theta over square root of 6 times theta is the same.
Okay, good. So there's our x, isn't it? Really, if we just include some parentheses here, and a lot of times this is helpful to do. When you have a sign of some stuff like that, it's a little bit, it's not unclear, but it could be visually confusing. If we do that, it clears things up, doesn't it? We know that all that stuff is the argument of the sign, and there it is in the bottom. So that's really acting as our x, isn't it? Okay. And so really, the only thing we got to deal with then is this theta going to 0. Well, what was our little trick there? If theta goes to 0, then what about the square root of 6 times theta? It's got to go to 0 also. And to me, I'll go back to this analogy of if I start here and cut my distance to the door in half with every step. If I start here, what if I started here? It's twice as far away. Doesn't matter, does it? I'm still cutting my distance in half with every step. So my initial steps are a little bigger, but the process is still the same and the limit's still the same, right? So multiplying by some constant number out, the variable that's going to theta doesn't affect anything, right? So we might as well just put a square root of 6 right there. Doesn't cost us anything, it doesn't change anything. So it works. How about this 4? What about that 4? That's going to be the answer, isn't it? It is just kind of hanging out. It's not part of that limit. What could we do with that 4 if we wanted to, being as it's a constant, to make it maybe a little bit more organized? Tateo's making that. What do you think? We could bring it out front, couldn't we? We could bring that constant out front because the limit is not acting on it. 4 is being multiplied by all this stuff, but only theta is being acted on by the limit. That's sort of the variable of the limit, right? So we could rewrite this in, if we wanted to, as 4 times the limit of this stuff up here. And we know that that limit, that's our special limit, that's the one that's going to go to 1. And that's kind of a slick way of showing that it goes to 1, that little arrow pointing to the 1. Okay, and so our answer is just 4. No big deal. Okay? Makes it questions on that. More than anything, that's kind of a nice way to just to show the work. All right. Okay, this is the one I wanted to get to more than anything. This is the one that I think people were having some trouble with. Suggestions on that one. And once again, remember what our trick is. Okay, incidentally, now if that's the special limit that we're relying on, does it matter? Being as the answer is 1 and the reciprocal of 1 is 1, can you think of another way I could express that limit that would also go to 1?
Well, it's theta over sine.
Okay, yeah, I could flip that, couldn't I? I could also write this as the limit of theta over sine theta as theta approaches 0. And of course, that has to equal 1 also, right? That's a good little trick, so we can remember that. So either one of those are sort of interchangeable. Either one works. So given that now, everybody see a trick here with how I could maybe break this thing up? There's a real temptation with this one to try to somehow get something to cancel within those signs. And I'm not saying it couldn't be done. It could be done, but that would be an arduous task to say the least. You'd have to rely on a long chain of trig identities, multiple angle formulas and all that kind of stuff to convert a sine 5x and a sine 3x into sines of the same angles. That's not the approach we want to take. Could be done. I'm not saying it wouldn't be, kind of an interesting challenge to try to do it, but we want to rely on this instead. Okay? Now the problem here, of course, is, and I'm sure you're looking at this saying, well, how's that going to work? There's a sine 3x, but there's no 3x. And there's a sine 5x, but there's no 5x anywhere. So we got to be a little creative with this one, algebraically. Any suggestions? Reese? Okay, split them up into separate limits. We're going to evidently have to have 2 separate limits here, right? Both of which are going to follow these patterns. I'll just have different thetas in my 2 limits. One theta is going to be a 3x, and the other one it's going to be a 5x, right? So let's do that to begin with here. So I've got the limit of, whoops. And I'm going to do that too. Right? Now, how am I going to get a 3x there and a 5x there? In fact, I think I'm going to move this. I didn't plan that very well. I'm going to move this down a little bit. I need a little more room to write. How could I need a 3x there, right? But algebraically, I can't change the expression, right? Function has to stay the same. So in order to keep things the same, I have to rely on my identity properties, right? Now, what's the identity number for multiplication? What do I multiply something by and not change it? 1, good. 1 in some tricky form, right? And then for addition, it would be adding 0, right? Well, that's probably not going to apply, but the multiplying one might. If I need a 3x on the bottom here, how could I get it there and still multiply the whole thing by 1? 3x over 3x, sure. But remember that when I'm multiplying a bunch of factors like this, I can choose to group those factors any way I want to. The order is really unimportant. So I'm gonna multiply by 3x over 3x. And one 3x is gonna go there, and the other one, how about if I just put it over here? Right? Because I'm okay to do that. I can group these things however I want to. And same trick with the 5x probably, right? Let's put a 5x here and a 5x there, right? So algebraically, they still cancel. I haven't changed anything. Okay, but now how does that help me? Well, yeah, look at that, sure. Now I've got the limit that I want here. I've got the limit that I want here, and 3x over 5x reduces algebraically, right? I can cancel those x's. So I've just got a 3/5 there. Okay? Now to be a little more rigorous about this, and I would argue that this probably isn't even that essential, but if you were, for example, on an AP test or on some, this would be probably an important thing to do. In order to get these two limits to be strictly following our plan, I need to have the argument of sine approaching 0, right? And this is kind of a little nitpicky thing, but how would you deal with this? My theta here is a 3x, and my theta here is a 5x. What would I probably have to do to make this look really legit and authentic? Well, okay, yeah, I mean, maybe something like that. But instead of, how can I pick a 3x or a 5x here? Well, I can't really do them both at the same time. So why not split this into two separate limits, right? And that's one of our properties of limits, recall. We said a while ago, and we don't use this very often, but we said that something like this. We said that if the limit of f of x as x approaches c is L, and the limit of g of x as x approaches c was k, I think, something like that, then the limit of f of x times g of x as x approaches c, we could split into separate limits, couldn't we? We could write that as the limit of f of x as x approaches c times the limit of g of x as x approaches c, which is just L times k. We don't have to. I mean, usually it's more convenient to just go straight from here down to there, right? But in this case, maybe we actually want to do that. Right, in this case, maybe I want to take this whole limit right here and break it off and separate the limit of sine 3x over 3x as what goes to 0? 3x times the limit of 5x and sine 5x as what goes to 0? 5x times my 3/5. And then, of course, this limit goes to 1, that limit goes to 1, and what's my answer? 3/5. Yeah, pretty tricky, huh? I don't call it genius, but it's pretty tricky. Okay? All right, what else?
I think like 3 or 4 often.
Say it again.
I think for the next 3 or 4 often is similar to that, but it's back to shuffling.
Yeah, okay, now this is, this one right here, well, yeah, a lot of them are sort of like that one. This is the one, this is an easy one, but I want to maybe real quickly just go through it because I don't think we actually did one like this. This is that other often forgotten standard form. We had 2 of them, right? We had 2 special limits. This is the one that I told you I never remember. I always just kind of derive it to myself every time I want to use it. I just go back to I just use that one. You have the freedom to do that if you want to. But you can also just remember it. If you have a good memory, maybe you just want to do that. I don't know. What's the other, does anybody remember what the other trig limit is? The one that would fit here. One that involves a cosine. 1 minus cosine theta over theta as theta approaches 0 equals No, that's the one, this one equals 0. Okay, so that's the one we want, that fits this one exactly. Now, you don't have to use it, you really don't. Instead, what I could do, well, let's just show how we could use that first. Makes it real simple. How could I fit that? It almost fits. Good. Sure, we'll just pull out a 1/14, couldn't we, right? I've got this 14 on the bottom, but the 14 is just being multiplied by the x, so I could just partition that off. In fact, I could even pull it clear out front, being as it's a constant. That 14, I could do that with times the limit of 1 minus cosine x over x as x approaches 0, and that we recognize as our standard limit, or as our standard form. That goes to 0, so what's our answer? 0, sure. Okay, the other way, we could do this one if we want to. You could also, anybody have an idea how we can do this one and use sine? What do you think?
I would like to.
Yeah. Sure, there you go. You could multiply by 1 plus cosine x, top and bottom. That's how I always do these. And then if we do that, on the top, what's that work out to be? What's 1 minus cosine x times 1 plus cosine x? 1 minus cosine squared x. Good. And now it becomes sine squared, right? And then we could just split that up the way we want to, right? We could combine one of those sine x's with the x, right, and push the other stuff into a different factor. So we'd end up with limit of sine x over x times what would be left? We'd have a sine x on top, I guess, right? And on the bottom, we'd have the 14 times 1 plus cosine x, right? And as x goes to 0, that one goes to what? 1, good. But over here, I'm going to get some number on the bottom, right? What do I get on top? 0. Sine of 0 is 0, so that one goes to 0. Make sense? Either way, I mean, this honestly, that's probably easier to do it that way if you remember the form. Okay. Okay, that one we just did one like that. That one, that's no big deal. We just fine with that. Okay, real quick, let's look at one of these. And then I think that's probably good. I think that'll get us going. Okay, now we talked a little bit about this, but we didn't do a lot of examples of these kind. When we're dealing with these trig limits, what happens when we run into tangents, cotangents, secants, cosecants? What's our best bet there? Say it again. Split them up into what? Sines and cosines. Good. When we have the composite trig functions, we want to always break them down into the fundamental trig functions, the basic ones, the sines and cosines. So then that tangent breaks up into a sine over cosine, right? So I could rewrite this as the limit of cosine theta on the top. I've got a theta on the bottom, and a tangent theta on the top I could rewrite as sine theta over cosine theta. And that works out great, doesn't it? Those go away, and we're done. I just got sine theta over theta, which is my special limit. Okay? Make sense? Okay, you think, is that probably enough to get you going, you think? Okay, let's go.
Sorry about that.
Oh, which one, number 8? I tell you what, let's go do it in the lab. Anybody that wants to, come up to the desk and I'll do it in the lab.